In this video, we're going to look at a problem that was requested by someone in the comments, so you guys feel free to request problems in the comments. Sometimes I'll see those comments and I'll get around to them. So it comes from the Indian Mathematical Olympiad, the year 1992, and it is question 8. So let's look at the statement of the question. We want to find all m and n which are natural numbers. In other words, they are positive integers, and they need to satisfy this rule. 2 to the nth power plus 3 to the nth power is a perfect square. So let's go ahead and look at some observations and hints. Maybe you guys can give it a go, and then we'll look at a solution. So the first hint is really an observation, and that is a 3, 4, 5 right triangle is an example of this phenomenon. Notice that 5 squared is equal to 3 squared plus 4 squared. Obviously, 25 is equal to 9 plus 16, but we can take this 3 squared plus 4 squared and write it as 3 squared plus 2 to the 4th. And this is actually a much bigger hint built into the statement of the problem than you might think, because often when there's a very simple example of this happening, the find all is really saying, show that this is the only one. And so maybe that's what we're going to end up doing here. Maybe there will be more solutions, but maybe there won't be more solutions. But the fact that there's a very, very simple example really points towards possibly that's the only solution to this problem. And then our next hint is that only certain numbers are perfect squares modulo n. And so we'll use that a couple of times in our solution. So for example, if we are working mod 3, notice 0 squared is 0, 1 squared is 1, but 2 squared is equal to 4, which is equal to 1. So 0 and 1 are the only perfect squares modulo 3. And then finally, we'll have this kind of obvious hint, but it's useful because we'll use it a couple times. And that says that if p is a prime and p to the k equals a times b, then a equals p to the I and b equals p to the j. In other words, a and b are both powers of this prime as well. Okay, so I'll clean this up, and then maybe you guys give this a go, and we'll look at a solution. Now we're ready to get on with our solution, and we're going to use that second hint first, which is looking at what the possible perfect squares modulo 3 in this case are. So let's notice that we have the following very, very simple calculation. 0 squared is equal to 0, which is congruent to 0 mod 3. 1 squared is equal to 1, which is congruent to 1 mod 3. And then finally, 2 squared is equal to 4, which is congruent to 1 mod 3. So notice, if we square all of the residues modulo 3, we only end up with 0 or 1. So what that tells us is that the only perfect squares mod 3 are 0 or 1. So it's impossible for 2 to be a perfect square mod 3. Great. Now what we want to do is take the condition that this is a perfect square, reduce it modulo 3, and see what we get. So let's see. We're going to have 2 to the m plus 3 to the n is equal to x squared. So we're assuming this is a perfect square. Now let's go ahead and reduce this modulo 3. That's going to give us 2 to the m is congruent to x squared mod 3. And so where did the 3 go? Well, let's recall that n is a positive integer. So this is 3 to the 1, 3 to the 2, 3 to the 3, so on and so forth. But that's congruent to 0 mod 3, so we can just get rid of that. Great. So what that tells us is that we have two cases. 2 to the m is congruent to 0 mod 3, or 2 to the m is congruent to 1 mod 3. But let's notice that one of these is completely ridiculous immediately, and that's this one. Notice this is a power of 2, but a power of 2 can never be a multiple of 3 because they're different primes. Great. So that means this is not a possibility. So that means that we have 2 to the m is congruent to 1 mod 3. Now let's go ahead and split that into two cases based on the parity of m. So maybe case number 1 is m is odd. Okay? So if m is odd, then we can write m is equal to 2a plus 1. But then that's going to tell us that 2 to the m, which is now 2a plus 1, is congruent to 1 mod 3. But now let's go ahead and reduce this left-hand side. That's going to be the same thing as 2 squared to the a times 2 to the 1. But notice 2 squared is congruent to 1 mod 3 by that. Then we have 1 to the a, so that reduces to 1. 1 to the a is 1, and then times 2, so that's congruent to 2 mod 3, which is obviously not congruent to 1 mod 3. So that means this whole possibility over here of m being odd is actually not a possibility. So let's go ahead and put that down here, not possible. And let's move on to the other case where m is even. And we've already seen that that will give us a solution by our observation before we started. But let's go ahead and check that everything works out just to be thorough here. So our next case will be m is even. So that means we can write m equals 2 times a. And notice that's going to give us 2 to the m is equal to 2 to the 2a, which is equal to 2 squared to the a, which is equal to 1 to the a, which is congruent to 1 mod 3. So everything is okay in this case. So in other words, we have reduced this to the problem where m has to be some sort of even number. So let's just set m equal to 2 times a for some natural number a for the rest of our solution. All right, let's go ahead and clean that up and then we'll move on. Up to this point, we've proven that this expression 2 to the m plus 3 to the n, it only has the possibility of being a perfect square if m is an even number. So that's what we've done. We've set m equal to 2a for some natural number a. Now what I want to do is see what that looks like inside our condition that this is a perfect square. So now we have 2 to the 2a plus 3 to the n equals, so that's going to be 4 to the a plus 3 to the n, so that's equal to x squared. So now our condition of 2 to the m plus 3 to the n being a perfect square is down to 4 to the a plus 3 to the n is a perfect square. And then this equation right here gives us some motivation that maybe we could reduce this modulo 4 and think about what are the perfect squares modulo 4. So let's go ahead and do that. We'll make a similar calculation to what we did before. So we have 0 squared, well that's obviously equal to 0, which is 0 mod 4. We have 1 squared, well that's 1, which is 1 mod 4. Next we have 2 squared, well that's equal to 4, which is congruent to 0 mod 4. So that's interesting. We have something called a zero divisor when we're working modulo 4. And then finally, 3 squared is equal to 9, but that's congruent to 1 mod 4. So notice here we have a similar setup to what we had when we were working mod 3. So in other words, 0 and 1 are the only perfect squares mod 4. Now we're going to use that fact to simplify again. So let's go ahead and reduce this equation modulo 4 and see what we get. So that's going to give us 3 to the n is congruent to x squared mod 4. And then like we did before, that's going to split off into 2 cases. One case where it's 0 mod 4 and one case where it's 1 mod 4. And notice the case when it's 0 mod 4 is going to be pretty simple again. So, but we'll write it out just to be thorough. So we have 3n is congruent to 0 mod 4. But again, this is clearly impossible because over here we have a power of 3, which is never going to be a multiple of 4, which is what it would take to be congruent to 0 mod 4. So this is immediately not possible. And that means that we have 3 to the n has to be congruent to 1 mod 4. Now we're going to play the same game that we did before with the parity of n. So in this case, let's maybe start with evenness. So let's say our first case is n is even. In other words, n equals 2b for some b. So that's going to give us 3 to the 2b, but that's equal to 3 squared to the b. But recall that 3 squared was congruent to 1 mod 4, so this is congruent to 1 mod 4. So everything checks out here where okay. Now, You can probably guess that we're not going to be okay in the other case, but let's just go ahead and see that. So case number 2, we have n equals 2b plus 1. So that's going to give us 3 to the 2b plus 1. Well, that's congruent to 3 squared to the b times 3 to the 1 using exponent rules. But just like before, that's going to be 9 to the b, which is 1. And so that's going to be congruent to 3 mod 4. So in other words, that is not a perfect square. So not a perfect square, so that means this is impossible. Which means case 1 is the only thing that can work out, which tells us that we know that n is also even. So now let's go ahead and clean this up. We'll add that to our so far part of our solution and then move on to the next part. On the last couple of boards, we have determined that m and n are both even. So in other words, we can write m as 2 times a and n as 2 times b, where a and b are some natural numbers. And now we can rewrite this object 2 to the m plus 3 to the n in the following way. So we have 2 to the m plus 3 to the n, so that's going to be 2 to the 2a plus 3 to the 2b, so that's kind of obviously 4 to the a plus 9 to the b, and then recall that we want that to be a perfect square. So the goal is to determine the a and b when that kind of object right there is a perfect square. Okay, so now let's see what we can do with that. So let's take this thing and rewrite it as 4 to the a equals x squared minus 9 to the b. And notice we can factor out this right-hand side using a difference of squares. So that's going to factor into x minus 3 to the b times x plus 3 to the b. So notice 3 to the b times 3 to the b is obviously 3 to the 2b, which is 9 to the b. Now the next thing that we want to do is use that third hint from way earlier in the video, and notice that this left-hand side of the equation is a power of 2, which means this right-hand side of the equation is also a power of 2. And so what we've done is we've taken a power of 2 and we factored it into 2 parts. And so what that tells us is that each of those parts are also powers of 2. So in other words, we have to be able to write x plus 3 to the b is equal to 2 to the c power, and x minus 3 to the b is equal to 2 to the d power. Now what I want to do is take this system of equations and eliminate the x's, and we can do that maybe by subtracting the second equation from the first equation, and let's see what we get when we do that. So x minus x is going to be 0. Then we're going to have 3b plus 3b, so that's going to be 2 times 3 to the b. And then here we're going to have 2 to the c minus 2 to the d. Now we can divide both sides by 2, and that's going to give us 3 to the b equals 2 to the c minus 1 minus 2 to the d minus 1. And now we want to notice the following thing, and that is that c is most definitely strictly bigger than d in this case, because here we have x plus 3 to the b, and here we have x minus 3 to the b. So that means that kind of obviously c is bigger than d. And another thing that we want to notice is that the left-hand side of this equation is odd. Well, it's a power of 3, so that's obviously odd, which that implies that the right-hand side of this equation is also odd. But if the right-hand side of this equation is also odd, that means one of these exponents has to be 0. But this fact up here, that c is bigger than d, means that this d minus 1 has to be equal to 0. So now we have d minus 1 equals 0. In other words, d equals 1. All right, the next thing that we're going to do is take this value of d, which we just calculated to be 1, we're going to pass it back up into this equation and see how that gets simplified and what we can do with that. So that's going to give us 3 to the b equals 2 to the c minus 1 minus 1. But now we're going to go ahead and reduce that thing modulo 3, and that's going to give us 2 to the c minus 1 is congruent to 0 mod 3. In other words, 2 to the c minus 1 is congruent to 1 mod 3. But then using an argument similar to what we did before involving perfect squares modulo 3, we see that c minus 1 has to be even. So let's go ahead and set c minus 1 equal to 2 times k because we know it's even. Okay, then we're going to go ahead and loop this thing back into this equation. Then we're going to go ahead and loop this thing back into this equation. So we're going to throw that in there, but we're running out of room, so let's maybe clean up the board and see what we've got. Okay, so we just ended up showing that 3 to the b equals 2 to the c minus 1 minus 1 for some value of c. And then we argued that that c minus 1 needed to be equal to 2k. Now what we'll do is we'll loop this value of c minus 1 back into this equation and see what we can do with that. So that tells us that 3 to the b equals 2 to the 2k minus 1. But now we're going to factor that as a difference of squares. So that's going to give us 2 to the k minus 1 times 2 to the k plus 1. Now we want to notice that this left-hand side of the equation is a power of 3, which means this right-hand side of this equation is also a power of 3. And then using the observation that we pointed out in our hints, that means that each of these must be a power of 3, and that's because 3 is a prime number. So what that tells us is that we can write 2 to the k plus 1 as 3 to the I, in other words, a power of 3, and 2 to the k minus 1 is also a power of 3, so we'll maybe call that 3 to the j. Now the next thing that we'll do is we'll take this system of equations and we will cancel the 2 to the k part. And we'll do that by subtracting the second equation from the first equation. So let's see what that gives us. So we'll have 2 to the k minus 2 to the k, that's 0. We have 1 minus minus 1, so that's obviously 2. And now here we're going to have 3 to the I minus 3 to the j. And then just like we had argued before, we know that I is bigger than j. And that's because 3 to the I is 2 to the k plus 1, and 3 to the j is 2 to the k minus 1, which means 3 to the I is bigger than 3 to the j. Okay, fantastic. Now since I is bigger than j, we can factor a 3 to the j out of this. So that's going to give us 3 to the j times 3 to the I minus j minus 1. But now we know 2 is a prime number, which means it can only factor as 2 times 1. And also we know that 3 to the j is an odd number. 3 to the I minus j minus 1 is an even number. So that tells us that this factorization is this thing being 1 and this thing being 2. So in other words, if 3 to the j is equal to 1, we see that j is equal to 0. So 3 to the 0 is 1. And this tells us that I minus j is equal to 1. And since j is equal to 0, we have I is equal to 1. Okay, great. So now let's go ahead and loop that back into these equations and notice that we can find out what k is. So if we loop these back into these equations, we have 2 to the k plus 1 is equal to 3. In other words, 2 to the k is equal to 2. In other words, k is equal to 1. Now taking k equal to 1 and plugging it back in here, we see that c minus 1 equals 2. But then if c minus 1 equals 2, that tells us that c equals 3. Okay, fantastic. Now what we can do is we can loop this c equals 3 back into this equation right here, and then solve for b. So let's go ahead and do that. We have 3 to the b equals, now it's going to be 2 to the c minus 1, so that's 2 squared, which is 4, minus 1, which is 3, and so that tells us that b equals 1. Okay, great. So now we're running out of room, but notice we've got one of our values, b is equal to 1, which makes n equal to 2. I'll clean up the board and then we will find out what a is, which will tell us what m is. Okay, we're almost there. We've just determined that b is equal to 1 in this equation up here. Now we can go ahead and solve for a and x. So that's going to give us 4 to the a plus 9 equals x squared. Now we're going to finish this off in a pretty similar way to what we've been doing this whole time, and that is with a difference of squares. So I'm going to go ahead and take this and write it as x squared minus 4 to the a equals 9. And then I can factor this left-hand side as a difference of squares. So that's going to be x minus 2 to the a, x plus 2 to the a equals 9. And now 9 factors two different ways. It factors as 9 times 1, or it factors as 3 times 3. But notice that only one of these factorizations is applicable here, and that is because everything involved is a natural number. You can check that x minus 2a is a natural number, that x is bigger than 2 to the a, and x plus 2 to the a is also a natural number. And this guy is strictly less than this guy. So what that tells us is that this is factoring with this one equal to 9 and this one equal to 1. So that's going to give us a system of equations to solve for a and x. So let's just spell that out. So we have x plus 2 to the a equals 9, and x minus 2 to the a equals 1. So maybe we'll first cancel the 2 to the a terms so that we can solve for x. And we can do that by adding these two equations. That's going to give us 2 to the x equals 10. In other words, x equals 5. And then finally, we can plug that up here, and we're going to have 5 plus 2 to the a equals 9. In other words, 2 to the a equals 4. In other words, a equals 2. Great, so it turns out there's only one solution, and that is when a equals 2 and b equals 1. In other words, when m equals 4 and when n equals 2, which happened to be the solution that we kind of already knew by a Pythagorean theorem on a right triangle. Okay, so this is a good place to stop.